Hey class, today we're going to be going over lecture 18. I'm ahead on the lectures. Obviously, like I record these probably maybe a week before they come out, or I post them right away, but a week before you really need to watch them. So I just got looking at the survey that I sent out after exam one. So I apologize that some of the lectures following exam one may not have reflected some of the suggestions that were made in the survey. If you haven't taken the survey, you can still go ahead and take it, kind of like an ongoing survey. Or if you just have other suggestions, you're free to like email them to me. The survey is just kind of a way to anonymously do it. And if you don't know where to find the link for the survey, it's in the announcements section of Learning Suite. So as far as the survey goes, a lot of comments I got about the lectures is that people would like to see more of the types of questions you'd find in Mastering Chemistry. Some people thought the questions in the lectures are easier than the Mastering Chemistry problems, and I think that's true sometimes. So I'm just gonna, before I do the lectures, I'm gonna go through the Mastering Chemistry assignments and just make sure that I'm covering questions similar. Obviously, I won't probably do, I'm not just going to cover all the questions in the homework, or else you might not be able to practice it on your own. But I'll make sure I'm at least covering some of the harder kinds of questions that you might see, so that we can walk through it in the PowerPoint. But again, not every single question will be covered in the lecture or anything like that. Just kind of, I just want to make sure that the content in the lecture will prepare you well enough to do the homework. And so I'm going to go ahead and try and do that. I think that was the main point that people said that they wanted to see different in the lectures. So if I missed something, email me and let me know. So, but it seems like the lecture format with the YouTube videos is working pretty good for people. So I'm glad to hear that. All right, let's go into this lecture 18 on energy and reactions. All right, loading the PowerPoint. Okay. Go ahead and try this quiz on your own. This is a review from the last lecture we did, lecture 17. Okay, hopefully you tried working this out. So let's go through this problem. So the question says, what is the percent yield if you produce 100 grams of carbonic acid? That's something we haven't learned how to name yet. Carbonic acid. When starting from 150 grams of CO2. And don't worry if you don't know the name of that. When I said we hadn't learned it yet, it's because I just want to make sure you don't feel bad if you didn't know how to name that one yet. Okay. Okay, anyway, sorry. Okay, so we're going, we produce 100 grams of carbonic acid, so 100 grams of this, when starting from 150 grams of CO2. Okay, so in the last lecture at the end, I kind of talked about how sometimes it's hard to recognize what kind of problem it is. This one's not hard because the question says right here, what is the percent yield? So this is a percent yield question. Percent yield, if you remember, let's see, is, so I'm trying to remember if the I goes before the E or after the E. And anyway, it's probably not important. Okay, so percent yield, we have actual over theoretical, okay? So again, the actual is always gonna just be given to us in the problem. So actual here is 100 grams, okay? So it's telling us that we did produce 100 grams carbonic acid. Okay, so for percent yield, we're gonna have 100 grams on top. And then theoretical yield is gonna go on the bottom, and that's gonna be based on the calculation that we do with this number here. Okay, so if we're using our little map, we go from grams of A up to moles of A, over to moles of B, down to grams of B. And if for some reason this map doesn't seem familiar to you, rewatch lecture 16 where I used it a lot. And I suggested that you kind of memorize that map. I think it'd be very helpful. Okay, so our A in this case is going to be our carbon dioxide, and our B is going to be the carbonic acid. That's our product. We're starting with 150 grams of carbon dioxide. So we need to go from grams of carbon dioxide to moles of carbon dioxide. So we're going to use the molar mass. Okay, and so just as a review, to calculate the molar mass of a compound, you're going to add up the sum of the molar masses of the elements. So the molar mass of carbon is about 12.0. The molar mass of oxygen is about 16.0. And it's okay to use these rounded numbers. That's fine. And we have 2 oxygens. Okay, so we have 2 times 16 is 32, plus 12 is 44. So the molar mass of carbon dioxide is going to be 44.0 grams per mole, every mole of CO2. Okay. All right, and then we're going to go from moles of carbon dioxide over to moles of the carbonic acid. So we just need to make sure that this equation is balanced. If it's given to you, usually it's balanced if it doesn't say to, but I always just double check just in case. So we have 1 carbon on the left side and 1 on the right. We have 2 oxygens on the left. Oh, sorry, we have 3 oxygens, 1, 2, and then 3, and we have 3 oxygens on the right. We have 2 hydrogens on the left and 2 on the right. So this is balanced, okay? It's a 1 to 1 to 1 mole ratio. So 1 mole of CO2 produces 1 mole of the carbonic acid. Okay, and then we need to figure out the molar mass to convert from moles of carbonic acid to grams of carbonic acid. So if we look at the molar mass, let me do it down here. So hydrogen is about 1.0. Okay, and we have 2 hydrogens in carbonic acid. We have 1 carbon, which again is about 12. And we have 3 oxygens, which is about 16. So 3 times 16 would be 48, right? Yeah. Plus 12 is 60, plus 1 is 61. Okay, so then we have 61.0 grams carbonic acid. Pen is delayed here. For every 1 mole of carbonic acid. Oh, the delay is driving me crazy. Oh well. Okay, if we cancel out our units, we're left with grams of carbonic acid. And whatever our answer is here, right, that's the theoretical yield. So that gets plugged into this equation. We multiply that by 100%, and we would get our answer. So let's walk through it with the PowerPoint here. Oh, 62 grams per mole. Oh, sorry. You all probably noticed I messed that up. Let's see. Yeah, 3 times 16 is 48, plus 12 is 60, plus 2, because there's 2 hydrogens, would be 62 grams. So anyway, I got the molar mass wrong. Okay, and that gives you 211 grams of carbonic acid. So that would go into our percent yield equation. 100 grams is what we actually get over 211 grams of the theoretical yield times 100% is 47.4% yield. Awesome. Okay, let's move on. So some of the goals of this PowerPoint are going to be to get a molecular picture of what is going on in a chemical reaction. Answer the question of why is heat required to start the reaction? Why is heat released or absorbed by a reaction? and be able to predict the heat of a reaction using calculations very similar to what we've done before in the last like 3 lectures. So we're going to build on that a little bit more. Okay, so in a chemical reaction, here's kind of what's happening. Okay, so if we had hydrogen gas and iodine coming together to form, this is called hydroiodic acid. These are the 2 iodines, right? They're bonded together in a covalent bond, and these are the 2 hydrogens that are bonded together. They're going to come together and hit each other. There's going to be a collision, okay? That collision breaks the bonds, so the bonds between the hydrogens are broken, and the bonds between the iodine molecules are broken. And then there's going to be a reformation of bonds, and so the new bonds that form are actually these 2 bonds. Okay, and so you actually have HI, 2 HI molecules that are formed, okay? That's kind of what's going on there. So there's a lot of energy involved in these reactions. Okay, so there's energy required to break the bonds that I was talking about in that first step. And that energy is called the activation energy, okay? So these are your reactants, okay? In the last example, this would be like your hydrogen gas and your iodine, okay? And then you have your products down here. It's like your hydroiodic acid, okay? So this is energy. If you remember back very early on in the class, we talked about chemical potential energy. So there's a certain amount of energy that's stored in the bonds of hydrogen and iodine, okay? And that's what this energy is right here. There's also a certain amount of energy stored in the bond between hydrogen and iodine in this molecule. I don't know if this graph isn't, this is just a general graph. So, you know, if you went up and looked this reaction up, you might find me wrong here, but I'm just using this as an illustration. So let's say that the energy that's stored in the hydrogen and the iodine bonds is at this level, okay? And then the energy is for the hydroiodic acid is down here at this level, okay? There's a higher energy up here from the bonds here. But you can't just roll downhill and convert from hydrogen to iodine into hydroiodic acid, right? This would be, you kind of imagine like a ball, okay? Imagine a ball here. A reaction doesn't work like this. It doesn't just go directly to another product, okay? Let me back up and show you what actually happens in a reaction. So in a reaction, you have your starting material or your reactants, and then you have your products. And what needs to happen is you first need to break bonds, right? If you remember that diagram from before. To break the bonds, energy is required. So if you imagine there's a little ball right here, it's going to take some energy to push the ball to the top of the hill, okay? If it's a small activation energy, it's easier to push, right? If this is just a small hill, it'd be really easy to push, and the reaction might just occur spontaneously using the energy from a collision or something like that. If it's a large activation energy, an external source of energy would need to be applied, like heat or something like that, in order to get that ball up to the top of this hill. So the energy that's required to get the ball to the top of the hill, or otherwise known as breaking the bonds, okay, that's called the activation energy. Okay, that's this difference between the energy state of the reactants at rest and the energy state of the reactants with their bonds broken. After you get to that point, right, if you push the ball here, all you have to do is let the ball roll down, and it's going to convert into the products. Okay, so this part would just kind of, that actually would release energy, okay? So if you imagine there's a lot of potential energy stored in this ball at the top of the hill. As it moves down to the bottom, it's being converted into kinetic energy, so that potential energy is being released into a different form. I guess you could think of it as like that. main points to pull away from this, okay? Another comment I got in the survey about the lectures is people want to know kind of a recap every once in a while, or maybe at the end I'll do a recap of what's really important to pull from the lecture, okay? So know that breaking bonds requires energy and that forming bonds releases energy. Okay, so if you looked at the example here in this last one, right? Breaking bonds is requiring energy to push the ball to the top of the hill. Energy is released as the bonds form to form new products as the ball rolls down the hill, okay? The heat of a reaction, you'll sometimes see it called, well, that's not a straight line, oh well. The heat of a reaction, sometimes it's called enthalpy change, okay, delta H, right? Delta we've seen before with delta T, right? Delta T is just a change in energy. Delta H is a change in H, okay? H represents the heat of a reaction or enthalpy, okay? Those are two terms you'll hear about for that, okay? And the whether it's positive or negative tells us if heat is absorbed or released during a reaction, okay? So an example, let's see if I show on here, okay? Example is if we look at like an energy diagram, what we saw before, look like this, right? So this is the product, or sorry, this is the reactants, and down here is your products. Okay, so let's say it took a little bit of energy to move the ball up the hill, right? And then it released all of this energy, okay? Where was I going with this? Oh yeah. So in this reaction, the difference in heat or the difference in energy is going to be this much, right? So energy is released in this reaction. So if we just use some number like 10 and 1 or something, okay? Remember that delta H is going to be a heat of products minus heat of reactants. If you remember, delta T was the final temperature minus the initial temperature. It's the same thing here. Delta is final minus initial. So delta H is the final energy of the products minus the initial energy of the reactants. So in our case, in this example here, we would have delta H of the products is down here at 1. So we'd have 10 minus 1. So our delta H would equal negative, oh, sorry, not negative. I made that backwards. Okay, delta H of the products is 1. Delta H of the reactants is 10. So that would equal negative 9. Okay, so that's our delta H. Okay, so negative delta H is energy is released, right? Okay, the other example you could look at is something like this. Okay, so in this case, let's just use 10 and 1 again. It takes a lot of energy to break the chemical bonds and to bring the ball to the top of the hill. And there's just a small amount of energy that's released when you form the products. So overall, if you look at the delta H of the products, we're at 10 minus the delta H of the reactants, which is 1. This is a positive 9 is our delta H, okay? So this means that overall in the reaction, energy was absorbed, or you could say energy was required, okay? And those are the kind of the two general pictures there that you have for reactions. Okay, go ahead and try to do this little quiz that you should have got from reading beforehand. Okay, let's go ahead and move on. So if a reaction absorbs heat, right, this is where I talked about the one that looks like this. Okay, the energy of the energy of the products is greater than the energy of the reactants. This overall requires energy for this reaction to happen. These are called endothermic reactions, okay? The opposite, which looks like this, right, where we have an overall release of energy, is an exothermic, okay? So this is endothermic up here because it requires heat or absorbs heat, and then exothermic is when it releases heat, okay? You can think of like exhale as when you release, breath. So exothermic releases energy. There you go. Okay, let's look a little bit more at these two reactions. So we have an exothermic reaction. Again, the energy of the products is lower, okay? So we have an overall release of energy, okay? If we're releasing energy, we can think of energy as a product of the reaction. And so we could write the reaction. This is kind of what you're used to seeing in a chemical reaction. And we can think of heat as a product as well for a reaction that releases heat, an exothermic reaction. You have a negative delta H, like we saw before, right? That's because delta H is products, is the heat of the energy of the product minus the energy of the reactant, right? So again, if we use the 10 and 1 example, we have 1 minus 10 equals negative 9. Okay, so negative delta H releases heat. Okay. Pretty much everything, the opposite is true for an endothermic reaction. The energy of the products is greater than the energy of the reactants. And we can consider heat as a reactant in the chemical equation because it's being required for the reaction to happen. So it's kind of like a reactant in the chemical equation. And you have a positive delta H. We talked about that. Okay, so now we're going to mix the calculations we've been doing, stoichiometry, if you remember that funny word, and heat. So we should be able to predict how much heat will be released or absorbed by a certain chemical reaction given a certain amount of starting material or something like that. So we need to know delta H for the reaction, and then we need to know how to use it, right? So here's an example. This is a reaction where you combine hydrogen gas and oxygen gas and you form water. So we have a negative delta H here, right? Delta H is negative. So if we looked at a reaction diagram, that means it would look something like this. An exothermic reaction, it's releasing energy. So we can think of this delta H as a product of the reaction. We could write it like this, okay? You might notice like the negative sign here and the positive sign here. Don't let that confuse you too much. The negative is really just telling you it releases 572 kilojoules per mole. So when you put it in the chemical reaction, you're not going to be subtracting it, right? It is 572 kilojoules is a product of the reaction. So here it's kind of written as a positive number, but don't let that confuse you too much there. So now we basically have a balanced chemical reaction, and we can do calculations just like we've done before. So when 2 moles of hydrogen react, right, we're going to form 572 kilojoules, right? You can think of it as like it's gonna release 1 unit of 572 kilojoules, I guess. When 1 mole of oxygen reacts, again, 572 kilojoules are released because there's a 1 in front of this oxygen. And then using the 2 in front of the water, we could say when 2 moles of water produce, 572 kilojoules of heat are released. So you can see, just like we did before, we can form these conversions, okay? We can convert between moles of water and heat, or moles of oxygen and heat, if we consider this to be one of the products of the chemical reaction. Okay, so here's an example. These are similar to the examples, at least the last few on the Mastering Chemistry homework. So if we say, let's say we burn 10 grams of hydrogen gas, okay? And we want to know how much energy is released in this reaction of burning 10 grams of hydrogen gas. So if you like that map that I drew, grams of A, we can go up to moles of A. And then from moles of A, we can go over to, generally we can go to moles of B, right? In this case, we're not really going to moles of B, we're just going straight to heat, okay? So I guess there's a different variation for this kind of problem. Okay, so to go from grams of A to moles of A, or grams of hydrogen to moles, we're gonna need the molar mass. So 2.02 grams per mole for hydrogen, because there's 2 hydrogens there. And then, yeah, I should have the labels here for every 1 mole of hydrogen gas. And then for every 2 moles of hydrogen gas, we produce 572 kilojoules of energy, right? Like we looked at in the last slide. And that takes us from moles of A to heat basically right away. And then we can say that we have 1,420 kilojoules of energy are released when you burn 10 grams of hydrogen gas. And you could do this for oxygen. It's going to be very similar, right? It's just a different mole ratio because oxygen has a 1 in front of it as the coefficient in the chemical reaction. And yeah, one thing sometimes people get maybe confused on is this is a negative number, and again here you have a positive number. So most of the time, you know, it's going to be like in a test situation, you're probably just going to look at the answer choices and see how it's being reported. But if the question is asking how much energy is released, you don't need to use a negative number, right? Because it is releasing 1,420 kilojoules. If the question asks like what is delta H for the reaction, then you'd probably use a negative number in that case. So those are the 2 times. You might have to switch between like positive and negative or something, but generally the question just says how much heat is released, and you'll just put a positive number most of the time. Okay. All right, go ahead and pause the lecture at this point and try and do this problem. All right. So let's go ahead and try it. The following decomposition reaction is endothermic and has a delta H of 92.2 kilojoules per mole. Okay, so we didn't really need the problem to tell us it was endothermic. We could figure that out on our own because delta H is positive, which means the reaction is endothermic. Because it's endothermic, that means we could write the heat as a reactant, right? So 92.2 kilojoules per mole. When we're putting in this, we're just going to write kilojoules because all these coefficients basically standardize it to 1 mole, if that makes sense. All right. Question now that we have this is how much hydrogen is produced if the reaction absorbs 200 kilojoules of heat? Okay, so now we're kind of going backwards. So if you looked at the, I guess the heat version of this map is grams of A to moles of A over to heat, right? And of course we could go the opposite with all these as well. So from moles of A to heat, we're going to need to use the conversion between moles and heat. So that means we're going to need a conversion between hydrogen gas and heat. So we can say that for every 3 moles of hydrogen, we are producing 92.2 kilojoules of heat, right? And we could flip these if we need to at some point. This is just a conversion. Okay, and that 3 comes from the coefficient here in the chemical equation. All right, so let's start with heat. So we have 200 kilojoules of heat. Using this conversion, we convert from heat over to moles. Call it the heat conversion, I guess. So 92.2 kilojoules. We want that on the bottom, so it cancels out the kilojoules on the top over here. To 3 moles of hydrogen. Okay, and then 1 mole of hydrogen weighs 2.0 grams or 2.02 grams if you want to be specific of hydrogen. Okay, and that would get us to the answer. So we went from heat to moles using this conversion, and then we went from moles to grams using the molar mass. Okay, that would give us our answer for that question. Cool, nailed it. Okay, here we go. Go ahead and pause the video and try this one as well. Okay, we're back. The decomposition of hydrogen peroxide is exothermic with delta H equals negative 196 kilojoules per mole. Again, we don't really need to have the question tell us it's exothermic. just because it's a negative value tells us right off the bat that this is an exothermic reaction. If it's exothermic, that means heat is one of the products of the reaction. Okay. Now the question says, if 200 kilojoules of heat is released when 100 grams of hydrogen peroxide decomposes, what is the percent yield? All right, mixing some ideas here. Hopefully you're seeing that questions could be anything. The really important thing is that you learn the concepts here, and you should be able to step through these problems. And in my opinion, that's what chemistry is all about for a lot of you guys. You're not going to really ever do this again, these types of questions, but you will need to solve problems, and that's why it's fun. Okay, so percent yield. So we know the percent yield equation. Oh, it is I before E. I messed that up at the beginning. I deeply apologize. Okay, actual over theoretical. Okay. Okay, so actual yield. So this is usually given to us in the problem, right? So here it's kind of hard to see, but actual yield is going to be a certain amount of product that's produced. The question, the only product that it gives us is, it says 200 kilojoules of heat is released. So our actual yield, again, we're considering heat as a product, is we're yielding 200 kilojoules of heat from the reaction. That's our actual yield of heat that we got. So now we need to calculate the theoretical amount of heat that would be produced if we have 100 grams of hydrogen peroxide to decompose. So that's our reactant. So this is going to be using our heat map here. Moles of A over to heat, right? Okay, so grams of A is going to be grams of hydrogen peroxide. So we have 100 grams hydrogen peroxide. We can convert from grams of hydrogen peroxide to moles of hydrogen peroxide using the molar mass, which would be 34. For every 1 mole of hydrogen peroxide. Okay. Then we can, so that gets from grams to moles. We can go from moles to heat using the heat conversion. So using the chemical equation, we see that 2 moles of hydrogen peroxide produces 196 kilojoules of heat. Okay, so that's going to give us our theoretical yield at that point. So I'm going to let the slide do the rest of the work here. So that's 288 kilojoules. Okay, so that is our theoretical yield of how many kilojoules we should be getting out of this reaction. Multiply that times 100%, right? And you're going to get your percent yield. So that's what we have down here. Percent yield is 69.4. So that if that problem threw you off at the beginning, just remember that heat can be treated as a product in an exothermic reaction, and it can be treated as a reactant in an endothermic reaction. I think that was the main idea there to remember. Okay, we have made it through that lecture. So I guess just as a recap, right? I think I had very few slides, and most of the stuff in there is pretty important to remember. But the 2 slides on like endothermic and exothermic reactions, where it says, you know, like endothermic is has a positive delta H, heat is a reactant, right? That's important. And I think it's important to also be able to well, I think it's definitely important to be able to recognize if you see one of those graphs with the curve, to be able to notice that that's a endothermic or exothermic reaction curve. And then also like those last couple questions, being able to use the heat in a chemical equation and then use stoichiometry to solve the problems is going to be something you're going to come across definitely in the homework and on the next test. So, all right, hope you have a great day.